There is a marker at the front of that table. It seems really obvious because you're watching this video, but the marker is not going to be there for very long because I'm going to take this tennis ball and I'm going to roll it into the marker, and it's going to knock the marker off of the table, just like that. And while you're probably wondering why it takes a physics teacher to show you that I can use a tennis ball to knock a marker off of a table, there's actually something really interesting that happens right there. Because you have a marker and you have a ball, and we can both identify that they are either moving or they've got a constant velocity and things. We can use things from Unit 1 to describe the way they were, but we can't use anything from Unit 1 to describe why they are acting the way that they do. And that's where Unit 2 comes in. Unit 2 is about why things move, not just how they move. So we'll talk about things like forces, like the force that the ball applied into the marker, and how forces change the motion of an object, like how the marker was stationary and then all of a sudden it started to move. But before we can start talking about forces, we need to talk about the guy that kind of started the idea of forces. And we're going to deal with this guy named Isaac Newton and his 3 laws of physics. This is Isaac Newton. I mean, look at the guy. He's got the long hair, the distinctly English persona, and it turns out he is one of the most influential mathematicians and scientists of all time. And the reason that we talk about Isaac Newton the way that we do is that he took the idea of objects interacting between each other and he made this into a popular science. But before he did that, he had to do things like invented the entire mathematics of calculus, or he figured out how light gets to bend as it goes through glass, and he created the entire science of optics. So this guy winds up being really, really important in the entire context of science. But when we're talking about physics in specific, he really gets down to breaking the universe into 3 laws. So what are those 3 laws? It's a great question. Let's go ahead and start taking a look at them. Isaac Newton's first law of motion is the one that kind of gets off as being the most obvious. And it says something like this. An object in motion tends to stay in motion, or an object at rest tends to stay at rest unless acted upon by an outside force. And this one seems really, really obvious, like I said. But I want you to take a moment and think about a ball rolling across your floor. You know that eventually, even if your floor was an infinite length in one direction, eventually that ball would stop. And this is the way that in Isaac Newton's time, everybody viewed things, is that an object in motion would eventually come to a rest. And so when Isaac says, no, an object in motion will continue doing whatever it's doing unless acted upon by an outside force, people looked at him and he thought it was kind of crazy. So it's not immediately obvious. And that's because Isaac Newton said, wait, there must be something slowing the ball down. And so he comes up with this idea of friction, an idea that later gets proven by other contemporaries. And so that's kind of Newton's first law of motion. Now, Newton's second law of motion is equally important. And Newton's second law of motion comes down to something like this. The amount of force that it takes to move an object is proportional to the size of the object, or how fast you want it to go. So let me go ahead and kind of put that in more common language terms. If I have a really, really large object and I want it to move fast, I want to change its position quickly, I need to apply a lot of force to it. If I apply that same amount of force to a much smaller object, it will accelerate a lot faster. And so think about this in terms of like a football player hitting, I don't know, an 85-pound freshman. Okay, so you've got a giant football player, a very, very large mass. The small freshman is not going to change the velocity of that football player much. They will not cause the football player to undergo an acceleration. But if that same football player runs into something like a truck, the much more significant mass of the truck is going to change the velocity of that football player by a much larger amount. So basically it comes down to I need a lot of force to change the acceleration of a very large object, or I need a much smaller force if I want to change the acceleration of a much smaller object. So that's force is equal to mass times acceleration. That's kind of his second law. Now, the third law is the one that gets quoted the most and understood the least, and is the idea that for every action, there's an equal and yet opposite reaction. And so if I have, for instance, my little pork plushie here, Mr. Bobinski, if I go ahead and I take him and I drop him onto the table, you'll see he kind of bounces as soon as he hits the ground. And that is because as he falls down onto the table, and we kind of do this in slow motion, as soon as he hits the table, he applies a force into the table. And the table, in response, pushes a force back up into the plushie. And that's what we call a reactive force. So that's Newton's third law of motion. For every action, there is an equal and opposite reaction. Means every time I do something, something is happening in response. So if I suddenly sit down on this chair that I'm sitting in right now, the chair begins to press up. That is that reactive force. Now, I keep using the word force as if it's supposed to mean something to you already, and I'm not talking about some mystical power, the ability to lift objects with your mind or anything like that. In physics, force is a very, very real term that we use to describe anything that changes the motion of an object. And there are lots of things that could change the motion of an object. So for instance, when I rolled the ball and I hit the marker, the ball was applying a force into the marker. We can call that like the applied force. Okay, there are things like the gravitational force. So if I take the plushie and I drop it, gravity is what's pulling the object or the plushie down. That's our gravitational force. I can sit here and I can lean into the table as much as possible, but the table keeps pushing back on me and it stops me from falling straight through the table. That's what we call the normal force. It's the force that stops objects from falling through each other. So there's lots of different forces that we have to take into account when we want to get a complete picture of what's happening for something. But the big thing that I want you to take away from this video, if there was kind of one statement that I have to highlight, even if you don't remember all the cool things about Isaac Newton, is that forces change the way an object is moving. Forces always create acceleration. So whether an object is speeding up or it's slowing down or it's changing direction, there's always going to be a force at play every time that you see an object changing the way it's moving. And that's the big thing about this week. Now, your assignment for this week is fairly simple. You're going to find an example of an object that is moving, and you're going to try to describe all the forces that are acting on it. So before you get to that assignment, I encourage you to go ahead and take a look at the notes where I go into more detail about what the different types of forces are and things like elasticity and torsion and other things that we can do to an object with a force. So hopefully that helps you. I hope to see some of you in class soon, and good luck with this week's assignment.